Thank you so much. So thanks everyone for joining this talk, and thank you, Kai, for the invitation and the nice introduction. So today I would like to talk about learning augmented algorithms. Let me start by giving a high-level idea behind this area. So in theoretical computer science, we design algorithms and we evaluate them based on the worst case analysis. So it's good, it's robust, we know what will happen in the worst case, but it's too pessimistic. On the other hand, machine learning algorithms, practically speaking, informs well, so they are efficient, but there is no guarantee how bad they can be in the worst case. So now the question is that can we get best of both these worlds? And learning augmented algorithm answer this question positively. Let me give you a few examples and explain where and how we can use this area. So consider online algorithms area. So in online algorithms, we do not have entire data in the beginning and data arrives over time. And we should make some decision and we evaluate these algorithms using competitive ratio. Now we can ask for some prediction about this future data that we have no information about them right now. And in case they are good, in case they are accurate, we would like to improve the competitive ratio of our online algorithm. But also we would like to have robustness against any bad prediction. Another area that we can use these predictions and algorithms with prediction is mechanism design. So in mechanism design, we have some strategic agents. They have some private data that they can lie about them. And we are looking for truthful or strategy-proof mechanisms, which means that we want to design a mechanism in which no agent has incentive to lie. So we can ask for prediction about this private data that agent can lie about it. And hopefully, ideally, we would like to improve the approximation factor of the truthful mechanism in case of having good prediction while being robust against any bad prediction. Another area that we can use this idea is voting. In voting problem, we have set of voters and set of candidates, and we only have access to the rank list of the voter and not about their actual utilities about the candidates. So what if we can get some prediction about this utility? Can we improve the performance guarantee in case of having good prediction or not? And there are many more areas, including even offline algorithms that we have all the data about them. But we can ask for prediction about the optimal solution and improve the running time. Well, now that we saw some example, let me formalize the setting. So in this setting, we have a set of prediction, but we do not know the quality of this prediction. This is a key point of this area. Therefore, we need to define a prediction error. We call it eta here. And we are looking for three main properties in this area for these algorithms. First, as I said, we want to be robust. We want robustness, which means that we want to lose only constant factor if our prediction is so bad. Look at this plot. We have performance guarantees in one axis and prediction error in the other one. So assume that the green line represents the algorithm without prediction. Now, by robustness, it means that we want our performance guarantee to be bounded by the red line, which is only constant factor away from the green line. But moreover, we want to have consistency, which means that if our prediction error is 0, we want to perform better than algorithm without prediction. So we want to be below this line, the green line. But ideally, we would like to have smoothness, which means that we would like to have the performance guarantee, which degrades gracefully with the quality of the prediction. So to summarize, we are looking for an algorithm with a performance guarantee that looks like this purple line. If the prediction error is 0, we want to be below the green line. And in any case, even in the very bad prediction case, we would like to be bounded by a red line. Well, this is a recent area introduced in 2018 by Likoris and Vasilvitsky. There are many fantastic work every week in this area. I just mentioned few of them in this slide, which is most relevant to my talk, but you can check all the papers in the website called OPS. In this talk, I would like to focus more on the learning augmented mechanism design. As I said, in this area, we want to design a strategy-proof mechanism. So we have some strategic agents, they have some private information, and we want to design a mechanism which is strategy-proof, which means that no agent has incentive to misreport her data. And our goal is to get some prediction, of course, and improve the approximation guarantee of these strategy-proof mechanism using these predictions. Well, I would like to explain this area with a specific problem called single facility location problem. In this problem, we have a set of strategic agents. Each agent has a location as a preferred location, and we want to open a facility. Think of it as a supermarket. Of course, each agent has a Euclidean distance from this facility. And the goal is to minimize some social cost objective. Well, the two famous social cost objectives are egalitarian social cost, in which we want to minimize the maximum distance of this agent, and utilitarian social cost, in which we want to minimize the sum of all distances. In this talk, I would like to focus on egalitarian social cost, which means that our goal is to minimize the maximum distance of the agents from the facility. Well, let's consider the line setting and deterministic setting. So basically, we have a set of agents on the line, and we want to minimize the maximum distance. The optimum solution basically should put the facility location in the middle of the two extreme agents, the leftmost one and the rightmost one, to minimize this objective function. And in two dimension, in Euclidean plane, it's sufficient to consider the minimum enclosing circle and put the facility on the center of this circle. Well, fine, we can find the optimal solution, but are these mechanisms strategy proof? Well, let me remind you again what is strategy proofness. Here in this problem, the location of these agents are private. So we do not have access to that. They report it to us. And we want to design a mechanism that no agent has incentive to misreport their date, their location. Well, let's consider the optimal mechanism on the line again, in which we just put the facility in the middle of the two extreme agents. Since only the two extreme agents defined this mechanism, we can ignore all the other agents. And now I want to show you that this mechanism is not strategy proof. Well, for example, the leftmost agent can lie about his distance to the left and bring this facility location, this supermarket, closer to him. Well, he could improve his cost, and therefore he has incentive to misreport. So this mechanism is not strategy proof. Now the question is that, what do we know about strategy proof mechanisms? What is the best approximation factor we can get in strategy proof mechanism? Well, again, in the line setting, in a deterministic setting, we can return the median agent. We can show that this mechanism is strategy proof, and we can also show that by returning any agent, we can get to approximation. And they also proved a lower bound that showed that we cannot ask for anything better than to approximation in this setting. Perfect. Now, what about randomized setting? Can we get a better approximation factor there? The answer is yes. There is a mechanism called LRM, which randomly assign these locations to agents. More specifically, it puts the facility with probability 1/4 on the two extreme agents and on the middle with probability 1/2. Well, you can show that this mechanism is strategy proof as well and obtain a 1.5 approximation, and there is a lower bound that match this approximation. Perfect. So We know everything in strategy proof mechanism. We have 2 approximation and 1.5 approximation in deterministic and randomized setting, and we know that we cannot ask for anything better. Now the question is that, can we improve this approximation factor using prediction? And what should we consider as a notation of the prediction? Well, in any problem, including the facility location problem, we can ask for different prediction setting. For example, in this problem, we can ask for prediction about all the missing data, which is the location of each agent. Or we can only ask about the optimal solution, which is the location of the facility at the end. Or surprisingly, there is another setting which we got interesting result in, that we just ask for the idea of extreme agents, not their location. We just need to know who are these extreme agents. Well, this problem has been studied by Agrawal et al. In deterministic setting with the prediction that they ask for the optimal facility location. They introduced a mechanism called min max p, in which basically they have prediction for the optimal facility location. And it's simple. They say that, okay, if it's in the middle of the 2 extreme agent, I just return it. But if it's outside on the left side, I report the leftmost agent. If it's on the right side and outside, and I just report the rightmost agent's location. They can show that this mechanism is one consistent, which means that it gives one approximation, the optimal solution, in case of having good prediction, because the facility should be in the middle of the 2 extreme agents always. And since they are not reporting anything outside this interval, they get 2 robustness. They extend their results into 2 dimensions by just running this mechanism on on each axis separately. Well, we studied this problem in the randomized setting. Together with Eric and Vasilis, we studied strategy-proof facility location in the randomized setting. So one way to evaluate all these learning augmented algorithms is to look at the consistency robustness trade-off. So consider this plot. We have consistency on y-axis and robustness on the other one. Well, we observe that using the previous predictions, using the previous mechanism, which we saw together, min max p, which we can get one consistency, 2 robustness, and LRM, which is the algorithm without prediction, which was 1.5 approximation, we can get 1 consistency, 2 robustness, and 1.5 consistency, 1.5 robustness. Well, we observe that we can merge these 2 algorithms using randomness and obtain this green line, which is between 1.5, 1.5, and 1 and 2. We show that actually this is tight. So even if we have the strongest prediction, which is the prediction that we have the location of all the agent, we cannot get anything better than this line. We study other prediction setting as well, and we showed the lower bound for them as well. And moreover, we studied this problem in Euclidean plane. So again, using the previous algorithms, previous mechanism, we can show that we can get this green line, which is between 2, 2, which is just a 2 approximation mechanism, and 1 and 1 plus root 2 robustness, which is the minimum bounding mechanism. But here, we have a positive result. We introduce a new mechanism called centroid of extreme agent, for which we have a prediction about the idea of extreme agent, and we could obtain 1.567 consistency and 2 robustness. We can again merge this mechanism using randomness with other mechanisms and get the purple line and other lower bounds in other prediction settings as well. Well, I told you about the learning augmented algorithms. We saw some example which area we can actually use these predictions. And we saw an example in mechanism design area, and I explained it through the facility location problem. Thanks a lot for your attention. I'm looking forward to answer your questions and discuss it further. in the discussion panel.